This lesson is a review of basic integration forms. At this point, you've had a good number of formulas that you really need to have committed to memory. It's sort of like when you're adding, you don't want to have to go look up the addition tables every time you need to add 2 and 3 together, do you? It will just help you when you look at an integral that you're trying to solve if you have those basic formulas in mind, because if it's not exactly that form, it will give you a hint a lot of times on what type of a substitution or what kind of technique that you might need to use in order to find the antiderivative. Now, I'm going to go through the list with you of the basic forms that you should have committed to memory. And if there's some of these that you don't know, you might want to make a note of these and spend some time learning those. Okay, our first basic integration formula, and these first ones you sort of do probably at this point without thinking about it. If you have a constant times a function, recall that you can pull that constant in front of your integral. So that's all this rule is. The constant times a function equals the constant times the integral of the function. The second rule is your sum and difference rule. If you have a sum or a difference of two functions and you're looking for the antiderivative, then you do the antiderivative of each term separately. And of course you add if this was addition, and you subtract if that was subtraction. These first two rules are pretty simple, okay? Now this one I always put in because sometimes students just sort of have a mental lapse and forget about this. The antiderivative of du, there's nothing in front of that. There's no function there, but remember what's understood to be there is a 1. And so whatever variable you're integrating with respect to, that's the variable you're going to get right here. The derivative of u with respect to u is 1. Okay? So the antiderivative of du is u, of course, plus some arbitrary constant. The fourth one is your power rule. Most students don't have any problem with that one. If you're finding the antiderivative of a power, you add 1 to the exponent. Recall whatever that new power is, you invert it and put it in front to take care of wiping out that constant. And this works for any power except -1. You can't have u to the -1. And of course the reason for that is because you can have a -1 plus 1 right here, could you? Okay. The next rule is your du over u equals the natural log of u, absolute value of u, plus c. Remember, this rule is also sometimes written as the antiderivative of 1 over u times du. Okay, so of course this is the same thing as what? U to the -1. So that one power that you can't do with the power rule, you can do with this log format right here. The antiderivative of e to the u with respect to u is e to the u plus c. Okay, your sine, the antiderivative of sine u is negative cosine u. The antiderivative of cosine u is sine u. Again, most of these first 8, most students pretty much know, but here's where they start not remembering. The antiderivative of tangent u is minus log absolute value cosine u. Remember, there's an alternative form of this one. It can be written as the log of the secant of u. Okay, but as long as you know one of the forms, you're in business. The antiderivative of cotangent u with respect to u is the log of absolute value sine u. The antiderivative of secant u with respect to u is the log of secant u plus tangent u in absolutes, plus your c. The antiderivative of cosecant u du is minus the log of absolute value cosecant u plus cotangent u plus c. And then these forms, most students don't have too much trouble with this because you know your derivatives. The antiderivative of secant squared u du is tangent u plus c. Antiderivative of cosecant squared u du is minus cotangent u plus c. Antiderivative of secant u tangent u gives you the secant of u plus your c. And the antiderivative of cosecant u cotangent u du is minus cosecant u plus c. And then these inverse trig function forms. The antiderivative of the du over the square root of a squared minus u squared gives you the arc sine of u over a plus c. Remember, a is a constant. U is where your variable is. The du over a squared plus u squared form gives you 1 over a arc tangent u over a plus c. And the antiderivative of du, where you have u in front of the square root of u squared minus a squared, is 1 over a arc secant, absolute value u over a plus c. These take a little work. The main thing here, some instructors don't have you memorize these, but the main thing is to remember these formats and know that you have a rule for them. Remember the difference between the arc sine and the arc secant is here the constant is in front and you're subtracting the variable format. That's reversed here, plus also you have that extra term in front right there. I don't think you probably realize there is this many different basic forms, but as I said, if you don't know these already, then you need to spend some time and make a list of them, whatever you need to do, so that you have those and you can work on learning those. So what this lesson is going to do is, as we look at each integral, we're going to try to figure out, can we put it in a form to fit one of these basic integration formulas? And of course, they're going to be all mixed up. In the lessons that you've had so far, like when you were doing these inverse trig functions, pretty much all of your problems was one of these forms, and so you kind of get in that habit of looking for it. Whereas when it's not all together, you may overlook that sometime. Now, I have put here to evaluate the following integrals, and you'll notice the three problems look a lot alike, and yet there are some differences here. I wanted to put all three up here on the screen at the same time to talk a little bit about your strategy when you see these different forms. Here's kind of how I approach these problems. When I see a quotient form, my first thought is, can I make this be 1 over u du? Because that's easy, that's a log function. So I think in my mind, if u is the denominator, x squared plus 4, what would du look like? Now, I don't usually write this down, I just kind of think about it. And so with this in mind, in particular, I'm thinking about that x dx stuff. I know I'm going to need an x to have the derivative of x squared plus 4. Well, if you look at this form, there's no x. So that does not look promising for a log form. If you look at this one, it's x squared, which is too many x's. The only one that has just the one x is that one. So I'm thinking this one is probably going to fit a 1 over u du thing. Okay? We'll look at these individually in a second. Now, between this one and this one, the other thing that I think about then, if it's not a log form, is I think about, is it an improper fraction? Recall, if the power in the numerator is greater than or equal the power in the denominator, it's termed improper. And in those cases, we want to divide. So I can look at this one and know that I want to divide that out and rewrite it first. That leaves this one. And so on this one, because it's not probably going to be this one and I don't need to divide it, this one I'm going to think about this form right here. You see this a squared plus u squared thing underneath there? See, this is squared and I know 4 is 2 squared. So I'm thinking this one might be the a squared plus u squared. Okay? Which will give me an arc tangent. So we're going to do each of these problems, but I wanted you to look at them together and see how I analyze each problem and think about, you know, what goes through my mind as I approach the problem, so I'll know how to solve it. Okay, so for this one right here, we have already talked about the fact that it's probably not going to be a log form because I know the derivative of x squared plus 4 would be 2x and I don't have an x. It's not improper, so I don't need to divide. So I'm going to try to fit it in that arctangent format, and this is why it's important to have this form memorized. I'm going to let u be x. Du then is the same thing, it's just 1 dx. I'm going to let a be 2 so that a squared is a 4. Notice if u is x, u squared is x squared. Okay? The 7 that's on top is a constant, so I can pull that in front first of all, and then I can bring that constant down. My x squared can be changed to a u squared, plus my 4 can be changed to an a squared, and my dx can be changed to du. Now, the actual formula that I showed you on your screen, let me sort of slide it over here, had du over a squared plus u squared. I have u squared plus a squared, and I have du over here. Is that really any different? Notice that this is over 1, so 1 times du can put the du up there. And whether I say u squared plus a squared or a squared plus u squared, it's the same difference, isn't it? So do you see how this really is the same thing as that form? So I know that the antiderivative is going to be 1 over my a arctangent u over a plus c, using my basic formula. All we have to do is bring this constant down. So 1 over a arctangent u over a plus my c. Okay, now we're going to substitute back in. What was a? It was a 2, so I have 1/2. Arctangent, what was u? It was x. A was 2, so x over 2 plus c. Of course, if you'd like, you can say 7 times 1/2 is 7/2, and I think I'm going to do that here. Okay, so it really helped us to analyze beforehand to know what form we were trying to get to solve this problem. Okay, on this one we said this one's probably going to be the log because the derivative of my x squared plus 4 involves an x, 2x dx. Solving for x dx, we have 1/2 du equals x dx. Okay, so as we've done before, 7 times x, so I can pull a 7 in front, x over my x squared plus 4 times my dx. Substituting in, this x squared plus 4 is on the denominator part, so I can put 1 over u. The x dx can be replaced with 1/2 du. You can pull the 1/2 out with a 7. 7/2 times the integral of 1 over u du gives you 7/2 natural log absolute value of u plus c, and then you can substitute back in for your u. Now, how easy or hard this is really depends on how well you know those basic forms. Okay, this one was the one that we talked about was improper since these powers are the same. So we know that we need to divide this one. Okay, so I think I've got room. I'll just do it right here. X squared plus 4. We're going to divide into 7x squared. X squared into 7x squared will go 7. Multiplying, I get 7x squared plus 28. I need to subtract this from this. Those change signs. That'll be 0. Notice 0 subtract 28 gives me negative 28. So my remainder is a negative 28, which I put over the divisor. So we're going to write this as 7 minus 28 over x squared plus 4 times dx. Okay? Now, the antiderivative of 7 with respect to x is just 7x, isn't it? Okay, so we've got that. Now, here I'm going to write this as minus 28 times the antiderivative of 1 over x squared plus 4 times dx. Okay? Now, this one is going to be that arctangent form like we just did. U is x, u squared is x squared, du is dx, a is 2, which makes a squared of 4. So we have 7x minus 28 times 1 over u squared plus a squared times du. So minus 28 times 1 over a arctangent u over a plus c. And we're almost done. 7x. Since a is 1/2 minus 28, I'm just going to go ahead and kind of do this. If that's a 1/2, then that's a minus 14. Arctangent. U was an x, a was a 2, so x over 2 plus c. Okay? Hopefully, with these 3 examples, you've seen how to sort of look at it in the beginning and think about what basic form might this look like. So it gives you a hint on what to choose for you or how to rewrite or something like that. The only way that you get really good at this is, first of all, know your basic forms, and secondly, practice, practice, practice. The more problems you do, the better you're going to get at it. Alright, well let's take a look at this one. Find the antiderivative of 3x plus 2 divided by the square root of 1 minus x squared dx. Now again, my way of thinking is this can't be a log because of the square root on this denominator. Log form doesn't have a square root down there, does it? So I'm thinking perhaps a power form, okay? So again, I think ahead. What is the derivative of this 1 minus x squared? It's negative 2x, isn't it? Okay? So if I were to let u be 1 minus x squared, du would be minus 2x dx. Now it involves the x, which I see right here. So what I'm noticing, first of all, I'm not concerned about the 3, but I am concerned about this plus 2, this extra term. So here's what we're going to do. Remember how we sometimes separate those numerators? So I'm going to write this as 3x over the square root of 1 minus x squared plus 2 over the square root of 1 minus x squared. We're separating those terms. Okay? Now this one has the x in it, so I'm thinking a U-Substitution. If I divide this both sides by negative 2, I get negative 1/2 du equals the x dx. So on this one, I'm going to put the 3 in front. I'm going to leave the x. I'm going to write 1 minus x squared to the negative 1/2. All of that's with respect to x. That's this one. Plus, on this one, I'm going to put the 2 in front. And I'm going to leave this one right now in the form of 1 over the square root of 1 minus x squared. The reason I'm not pulling this up in a power format is because I don't have an x. Okay, which I need to have du. Okay, well let's see what we can do on this one. This one I'm going to pull the 3 down. This is going to be u to the negative 1/2. The x times the dx is negative 1/2 du. Okay? Now, I'm going to kind of, at this point, leave this part over here. We're going to come back and pick it up in a second, but so you don't get confused with all the substitutions, we're going to finish this part right here. This minus 1/2 comes out, minus 3/2, antiderivative of u to the negative 1/2 with respect to u. This is a power, so we're going to bring down our constant. If we add 1 to our exponent, we get positive 1/2. If you flip that, you get a 2. So negative 3/2 times 2 gives you a negative 3u to the 1/2. And finally, substituting back in, you've got negative 3 times 1 minus x squared to the 1/2. So this first part, we've been able to follow all the way through. What are we going to do with this one? I can't use this substitution because I don't have an x up here that I would need to have my du part. Okay? So, think back again to these basic integrals involving your inverse trig functions. Look at this one. It has a square root on it. A squared, that's a constant, minus u squared. Look at what we have. We have a square root. 1 is 1 squared, and x squared. So I think we can get this arc sine form. So on this one, we're going to do a different substitution. For this one, u is going to equal x, du is dx, a is going to equal 1. That means we have 2, 1 minus, a squared minus u squared down here, and dx is du. So do you see how we have fit that exactly into this form right here? So we will pull our 2 down. We will get the arc sine of u over a. And I'm going to put my plus c. Let's keep coming down here. Plus 2. Arc sine. Now don't forget the u we used here was this one. So x over my a is a 1 plus c. We're just going to keep pulling that down. Arc sine, I don't need to write the 1, so x. And finally down here my final format. So I'm sort of doing this in 2 pieces and assembling my answer together. Notice a different U-substitution for this half as compared to this half because of what we ended up with. But we employed the technique of separating these 2 terms up here. Remember, this over this plus this over this, common denominator is these added together over the common denominator, going backwards. You should have seen that technique before. Now, this one is the integral of dx divided by the square root of 8x minus x squared. Now, I want to show you here that I have a square root down here, so not going to be a log form. The derivative of this thing under here would be 8 minus 2x. I don't have anything even close to that. So it's not going to be a power form because I can't get the derivative of this quantity under here. Basically, the only thing left that sort of looks like a square root in the denominator is this one we looked at a minute ago, right here. But this is not a constant squared. Although this could be a u squared, this is not a constant, so it doesn't look like this. So you might recall when you studied this lesson that sometimes we have to do some work in order to get it in the form that we want. We're going to take 8x minus x squared and complete the square, okay? Now, you may have learned to do this several different ways. I'm going to sort of do it this way. First of all, I like to rearrange it and put the squared term first. So this is minus x squared plus 8x. Remember, to complete a square, you need a positive 1 in front of that, so I'm going to put a minus sign here, x squared minus 8x. Notice at this point, if I distribute, I still have equivalent to what I started out with. Since I have a 1 here, half of this negative 8 is negative 4. If you square that, you get a plus 16. Now recall right here, if you distribute this negative, you get minus x squared plus 8x minus 16. So you need a plus 16 so that you have minus x squared plus 8x, and the minus 16 plus 16 cancels. Now, this x squared minus 8x plus 16 is x minus 4 squared. There's a negative in front of that. We have our plus 16. And then finally, I'm going to turn it back around and say 16 minus the quantity, x minus 4 squared. What I've been able to do here is show you that 8x minus x squared can be rewritten as 16 minus the quantity x minus 4 squared. Notice now I have a constant squared minus something else squared. So if we let u be our x minus 4, du is 1 times dx. If we let a be 4, then a squared is 16. Okay, so dx is the same thing as du. We have square root. 16 is a squared minus x minus 4 squared would be u squared. So that's our basic form. We know this is going to give us an arc sine u over a plus our c. And so we have the arc sine of x minus 4 over 4 plus c. I wanted you to see the difference between this problem and the one that we did just a second ago. If I can put that back up here a second. Notice on this one, the derivative of 1 minus x squared is a minus 2x, and I saw this x. So that sort of prompted me to split this thing up. Okay. Here, the derivative of 8x minus x squared is going to involve an 8 and also a minus 2x. I don't have anything that looks like that. So in this one, I went directly to the arc sine format, whereas on the other one, I split it up and then approached it from that standpoint. Find the integral of secant squared x e to the tangent x dx. Well, you've got all kinds of functions running around in this thing, but here's what I look at. When I see an e, the first thing I want to know is, can this be e to the u times du? So I look at the exponent on e, and I think, what's the derivative of that? Well, the derivative of tangent is secant squared. And look what you see right here. This is going to work out very nicely. If I let u be the tangent of x, then the derivative of u is secant squared x dx. So this part right here can be rewritten as e to the u. Notice the u is just the tangent, so it's e to the u. The secant squared x dx, which you see right here, can be replaced with du. A very simple, straightforward substitution. So the antiderivative of e to the u du is e to the u plus c. And then finally, I can just go back and substitute back in for my u, e to the tangent x plus c. Now, whenever I have e's, as I said, that's usually the first thing that I look for. Now, if I had looked at this and the derivative of this tangent x, which I know is secant squared, wasn't there, then I would have to try some other technique. Find the antiderivative of secant x plus tangent x, quantity squared, dx. Now on this one, because this is a quantity squared, sometimes I think, okay, if I have a quantity squared, can I let u be what's inside? But obviously, if I let u be secant x plus tangent x, the derivative would be secant times tangent plus secant squared, which I don't have. So this is not a basic u to the n du thing, which I would always look for first. If it isn't, then I think about doing some algebra. So basically this is a binomial that needs to be squared. Secant x plus tangent x times secant x plus tangent x. So if you multiply that out, you get secant squared x plus 2 secant x tangent x plus tangent squared x. All I'm doing here is just multiplying this out, squaring that binomial. If you need to do that, write the secant x plus tangent x times secant x plus tangent x and do the FOIL process if you don't know this shortcut way of squaring that out. Now, the reason that I am thinking this might be a good thing is because the tangent function has a derivative of secant squared. I can find the antiderivative of that. The secant function has a derivative of secant x tangent x. I can find the antiderivative of that. Now here's a problem. I don't know how to find the antiderivative of tangent squared. Now if that was just a simple tangent, I could do it, but not just tangent squared. So before I finish this problem, I'm going to think about an identity. So I'm going to leave my secant squared x plus 2 secant x tangent x. And you might recall that tangent squared x is equal to secant squared x minus 1. So I'm going to replace this tangent squared right here with secant squared x minus 1. Now this secant squared I can add with that one. So I have 2 secant squared x's. I have 2 secant x tangent x. And I have a minus 1. Okay, basically then I have a sum and difference of functions, okay? This 2 is a constant, I can bring it down. The antiderivative of secant squared x with respect to x is tangent x. Plus, I can bring this constant down. The antiderivative of secant x tangent x with respect to x is secant x. And the antiderivative of 1 with respect to x is an x, so minus x. And then of course I'm going to have my plus c. So once we squared it out and used that one identity to rewrite, then we had basic forms that we could do. Here's a list of some things to think about. Expand, basically that means to multiply out. That's what we just did on the previous example. Separate numerators. We did that a little while ago on one of our examples. Complete the square. We've done that. Divide improper rational functions. We've done that. Add and subtract the same quantity. We've not done that yet, but I will do an example in a second where we will do that, and I'll illustrate it. Use trig identities. We've done that. Multiply by a form of 1, and I've mentioned conjugate here, which I will show you in an example a little bit later doing that. And of course, your substitution. These are things to sort of have in the back of your mind when an integral is not fitting a basic format. What are some of the things that I can do to make it work? Okay? So, in addition to your basic integrals, think about these different techniques. Alright, so here's an integral. Find the antiderivative of 3x squared minus 7x divided by 3x plus 2 with respect to x. Well, here's what I think. Quotient form, the derivative of the denominator would just be a 3. I've got too much stuff up here for it to be just a 3. So it's not going to be a 1 over u du. Notice the powers. That power is bigger than this one. That's an improper fraction. So we need to divide this one out and then take a look at it. So we're going to divide 3x plus 2 into 3x squared minus 7x. Okay? Well, 3x divided into 3x squared will go x times. Multiplying, we have x times 3x is 3x squared. X times 2 is a plus 2x. Remember, we're going to subtract. Those change signs. So those drop out. Negative 7x minus 2x is a negative 9x. Okay? Well, 3x will divide into negative 9x negative 3 times. Multiplying by the negative 3. Negative 3 times 3x is negative 9x. Negative 3 times 2 is negative 6. Subtracting, we'll change our signs. Those drop out. There's a 0 here, so we get a 6 as our remainder. So plus 6 divided by 3x plus 2. So this integrand can be rewritten as x minus 3 plus 6 divided by 3x plus 2. Well, look what we can already do. The antiderivative of x is 1/2 x squared. The antiderivative of minus 3 is minus 3x. Now we are going to need to work on this one. I'm going to pull the constant in front. 1 over 3x plus 2 times dx. And do you see what I'm thinking probably? The derivative of this is a 3. So I can fix that. So I'm going to let u be 3x plus 2. du, it's 3 times dx. So dividing by 3, 1/3 du is dx. So let's bring this part of our answer down. 1/2 x squared minus 3x. Going to bring down our 6. This is 1 over u. dx is 1/3 du. So I have 1/2 x squared minus 3x. If you bring your 1/3 out here with that 6, 6 times 1/3 is a what? It's a 2. And the antiderivative of 1 over u with respect to u is the natural log of absolute value u. We'll put on our plus c. And we're almost home. We just need to replace that u. 1/2 x squared minus 3x plus 2 times the natural log of the absolute value of 3x plus 2 plus c. Did you notice that once we recognized that this is improper and we needed to divide it out, once we got it in this form, it turned out to work out relatively easily. Find the antiderivative of cotangent cubed x times cosecant squared x times dx. Well, we've got trig functions going on here, and they have powers. Here's how I approach it. What's the derivative of cotangent? Well, that's what? Negative cosecant cotangent? I'm sorry, negative cosecant squared. I'm thinking the other one already. The derivative of cotangent is negative cosecant squared. The derivative of cosecant is negative cosecant cotangent. The important thing that I notice here is the derivative of cotangent is basically this cosecant squared. So I'm going to try just a U-substitution here where I let u be the cotangent of x. du, as we said, is minus cosecant squared x. There's that cosecant squared x dx, so all I need to do is worry about that negative. So we'll multiply both sides by a negative 1. So cotangent x is u, so since cotangent was to the third power, u will be to the third power. And cosecant squared x dx can be replaced with a minus 1 times du. Of course, the minus 1 can come in front. And the antiderivative of u cubed with respect to u will be 1/4 u to the 4th plus your c. And sub back in minus 1/4 cotangent to the 4th x plus c. If you know your derivatives and you know your basic integral forms, this is an easy problem. Okay, well, we may need to get creative on this one. Find the antiderivative of 2 divided by e to the negative x plus 1 with respect to x. The reason I said we might need to get creative, it's a quotient. The derivative of the denominator, since that's an e, would involve an e, wouldn't it? The derivative of e to the negative x would first of all be e to the negative x, and then it'd be times the negative 1. I don't have another e to the negative x anywhere, so in this form right here, this is not a 1 over u du possibility. Remember that technique that we talked about that said to multiply by a form of 1? I'm going to do that. I'm not going to do conjugates yet. I'll show you that on another example. But I'm going to take this and I'm going to multiply by e to the x over e to the x. That's 1, isn't it? So multiplying this by 1 is still this. But it is going to alter the way this thing looks. I have 2 times e to the x in the numerator. Now, let's talk about this. When I multiply e to the x times e to the negative x, it's the same base, so we add exponents. So I have e to the what? 0. Plus 1 times e to the x is e to the x. Now, let me do just a little bit more work. 2 times this, I can pull the 2 in front. I have e to the x here. E to the 0 is 1 plus e to the x. Now look at it. What's the derivative of 1 plus e to the x? It's e to the x, isn't it? Now, if I let u be my denominator, du is going to be e to the x dx, and I can do a simple substitution. 1 over u, this e to the x dx is my du. So I have 2 times the natural log absolute value of u plus c, and then substituting back in the natural log of 1 plus e to the x. And by the way, this is one of those where they may leave off the absolute values because 1 plus e to the x is always positive. Why did I do this? Well, the derivative of e to the negative x plus 1 involves e to the negative x, and it's not up there. So, I got creative, multiplied by 1 in the form of e to the x. That gets me an e up there, and it also changes things down here so they get e to the x down here. I want you to realize if I had multiplied by e to the negative x, this would have ended up being e to the negative 2x, and it still would not have worked. So sometimes you have to experiment with things to see exactly what will work and what will not. The integral of 1 plus sine x divided by cosine x with respect to x. Well, the derivative of cosine is negative sine, but the problem is I have this 1 plus stuff here. I have an extra term. So we're going to try separating that numerator. 1 over cosine x plus sine x over cosine x. Okay? All right. How can you rewrite 1 over cosine? Well, 1 over cosine is secant, right? How can you rewrite sine over cosine? Well, that's tangent. The reason I'm doing that is because now we have a rule for all 6 of our trig functions. If you haven't memorized those, you need to do so. The antiderivative of secant x is the log of the absolute value of secant x plus tangent x. And the integral of tangent x is minus the log of the absolute value of the cosine of x. And then you can put on your plus c. Okay? Now, I will tell you this. Sometimes with logarithms, you will sometimes do some rewriting. A difference of logarithms, you can write one logarithm where you divide. Another possibility is you could take this as a negative 1 up as a power and invert this thing, and then that would become a plus sign, and then you would multiply. I'm not going to go into all the different forms that you could have on this one, but I want you to realize that there are other forms that the answer could appear in. So if you get aware of that when you're doing your homework and you're checking answers, you might learn to Look at your answer first and see if there's some way you can rewrite it to get another form to see if you're correct or not. Find the antiderivative of 1 plus e to the x quantity squared divided by e to the x with respect to x. I have a quotient form, but the derivative of this denominator is simply an e to the x. I have a lot more stuff up there, don't I? So we probably need to do some work here. Now, since this is quantity squared, we might expand. Remember, that was one of your techniques. Multiply this out. So we're going to square this binomial. 1 plus 2 times e to the x plus e to the 2x. Now, I might want to talk about that just a little bit. Some students get confused on that. 1 plus e to the x quantity squared means that you're doing this, doesn't it? So 1 times 1 gives you your 1. Your outside product is 1 times e to the x. Your inside product 1 times e to the x. When you multiply these last two, it's the same base, so you add exponents. X plus x is 2x. Of course, when you add these together, that's where that 2 e to the x comes from. So I want you to be sure you understand how I got this answer. So we squared out the numerator, and that's divided by e to the x with respect to x. Now, since this is a single term down here, we might try separating numerators. 1 over e to the x plus 2 e to the x over e to the x plus e to the 2x over e to the x. Well, let's see. I can rewrite this as e to the negative x. Here, e to the x cancels. I just have a 2. Here, this is the same base, and I'm dividing, so what do? You subtract exponents. 2x minus x is x. Well, you know what? I can do that, and I can do that, and I can almost do that. If I let u be negative x, du is negative 1 times dx, or minus du is dx. So this first one is the integral of e to the u times a minus 1 du. Okay? Now I don't need a substitution here. The antiderivative of 2 with respect to x is 2x. And the antiderivative of e to the x with respect to x is e to the x. I'm going to go ahead and put on my plus c down here. Here you're going to bring your negative out, and the antiderivative of e to the u with respect to u is e to the u. Let's copy down the rest of this solution here, and then we're going to sub back in. So minus e to the negative x plus 2x plus e to the x plus c. So we employed several techniques here, didn't we? We expanded, we multiplied out, we separated numerators, and we also did a U-substitution. Find the antiderivative of 2x divided by x squared plus 6x plus 9 with respect to x. Well, let's see. On this one, it's a quotient form, so I look at that denominator. The derivative of my denominator would be 2x plus 6, wouldn't it? Well, there's the 2x. What I don't have is the plus 6. Well, here's where we're going to add and subtract the same term. In other words, I'm going to write 2x plus 6 minus 6. Notice that's still just 2x. So technically, I have not changed anything. But I've created that 6 that I wanted to have the derivative of this down here. So we're going to separate right here. We're going to write one integral as 2x plus 6 over x squared plus 6x plus 9. And then we're going to have minus 6 over x squared plus 6x plus 9. Okay? This one, we're going to let u be x squared plus 6x plus 9. du is 2x plus 6, so I have the integral of du over u there, minus. On this one, I'm going to pull the 6 out front, and I'm going to write this as 1 over x plus 3 quantity squared. Notice x plus 3 quantity squared is x squared plus 6x plus 9. Okay? Now on this one, I'm also going to do a U substitution. Don't confuse the two U's. Here I'm going to let U be x plus 3. du is 1 times dx. Now on this one, I've got the natural log absolute value of U. Here I've got minus 6, and I'm going to pull this up as U to the negative 2 times du. Now don't let the two different U's confuse you. Substituting back in here, U was x squared plus 6x plus 9. Here we need to find an antiderivative. Let's bring down the minus 6. This is a power. So if we add 1 to the exponent, we get negative 1, which places negative 1 in front, plus c. Natural log, absolute value, x squared plus 6x plus 9. This will change to a plus 6 over u. I slid that u down under. And then finally we will replace this u. So I have the natural log, x squared plus 6x plus 9, plus 6 over this u, x plus 3, plus c. Now, because it's a quotient, I'm thinking log, so I mentally take the derivative. Is it up here? Nearly. So I fix it. Add and subtract the same term. Separate it. So this one's going to be my nice log form. Here, I just happen to notice that this was a perfect square, and then that can come up and be a power form. Very often on problems, you're going to be doing two different U substitutions. You can use different variables if you tend to get them confused. I just try to keep in mind which substitution goes to which problem. One more problem that I want to do for you. Find the antiderivative of 1 over secant x minus 1 times dx. Now this is a quotient. The derivative of secant is secant tangent, and that is nowhere to be found up there. So we're going to get creative. We're going to multiply by 1 in the form of secant x plus 1. Now, those techniques that I listed, sometimes we multiply by a form of 1, and I mentioned here conjugate. On this one, I'm using the conjugate of this. Conjugates, recall, look just alike except they have opposite signs. Now, let's follow through this and see how we get to our final solution here. 1 times secant x plus 1 is secant x plus 1. If we multiply these conjugates, secant x times secant x gives me secant squared x. The outside product is 1 secant x. The inside is minus 1 secant x, so those drop out. Minus 1 times a plus 1 is a minus 1. Okay? So we have secant x plus 1 over secant squared x minus 1 dx. Think identities. Secant squared x minus 1 is the same thing as tangent squared x. Okay? I have two terms up here. We're going to separate the numerators. Secant x over tangent squared x plus 1 over tangent squared x. Well, let's see. This is the same thing as 1 over tangent squared times secant, right? 1 over tangent squared is cotangent squared. So I have cotangent squared x times secant x. And 1 over tangent squared is what? Cotangent squared? Well, you may think we're never going to get anywhere, but I promise you we are. Okay, cotangent squared is cosine squared x over sine squared x. Secant is 1 over cosine. Cotangent squared is cosecant squared x minus 1. You probably think I'm going in circles, but I promise you I'm going to get to a point. This cosine will cancel one of those. So I have sine x to the negative 2 power times a cosine. And I can separate these as the integral of cosecant squared x dx minus the integral of 1 dx. Okay. I can find the antiderivative of 1. I can find the antiderivative of cosecant squared. And here I can do a U-substitution. Okay? I'm going to put my U up here. If I let U be the sine of x, du is cosine x. So, dx. Let me get that on there. So here I have u to the negative 2 times du. Do you see that? And then I'll be able to do that one. The antiderivative of cosecant squared is minus the cotangent of x. The antiderivative of 1 is an x, so that's a minus x. I'm going to go ahead and put my plus c. The antiderivative of u to the negative 1, if I add 1 to that power, I'll get a negative 1, so minus u to the negative 1 minus cotangent x minus x plus c. Of course, this is minus 1 over u minus the cotangent minus the x. And finally, substituting in, I have minus 1 over, remember the u is sine x, minus the cotangent of x minus x plus c. Now, if you'd like, you could write 1 over x as minus cosecant. Okay? Let me tell you kind of what I was doing. The original part, I tried thinking log. Just was not there because the derivative of the secant x minus 1 was not there. I know I need to write it differently. Since these are not squared or anything, there's no trig identity I can use. I decided to use the conjugate because I knew that would give me a secant squared, and I know there's an identity I can use with secant squared. So I used the conjugate here, got this form. Secant squared x minus 1 is tangent squared. Okay? Now, even here, I'm thinking, well, the derivative of tangent is secant squared. I don't have a secant squared. Okay? So I decided to separate these two. Okay? And then I just thought, well, let's rewrite, see what happens. So I changed this to cotangent squared times secant, brought this up as cotangent squared. I know there's an identity here, and I use my identities here. Finally, getting it down to where I've got a sine to a power with a cosine, so I can use a U-substitution. With this identity here, I know how to find the antiderivative of cosecant squared, and I got that nice constant. These problems can really be difficult, and it really takes a lot of practice for you to be able to work through some of these problems. Now, I've done a lot of different things here in terms of techniques. You may need to spend several times looking over these examples, and what you will see happening, honestly, is that you will start running across integrals that are very similar. So after you've seen me do some of these sort of creative things, as I've called them, in order to find an antiderivative, when you see an integral and you say, you know, that looks kind of familiar, I've seen something like that before, you go back and think about what did we do to work it out, and you can try that same technique on that integral. But you'll learn that these integrals do sort of appear alike in some instances, and you kind of get a feel for what to do. Again, I just want to emphasize, the better you know your basic formulas, it really helps because it sort of gives you an intuitive idea of what you're trying to get. Am I trying to get a log form? Am I trying to get an e to the u? Is this going to be one of those inverse trig function forms or whatever? Is it a power form? And so you get an instinct for that. And then the other thing is just practicing the techniques and keeping in the back of your mind, what are some of all those things that we did in order to rewrite an integrand? So I just want to wish you good luck. Just practice and really work on learning those integrals.